One of the things that you really have to know in order to understand stars is Virial Theorem, and it's particularly important for star formation. So here we go. Basically, Virial Theorem is a relationship between the gravitational potential energy that the cloud has and how that converts to thermal energy during the collapse of the cloud to a star. So let's start by assuming the star is made of an ideal gas. The thermal energy contained in that gas is given by the kinetic energy, which is the average per particle is 3/2 kT, and that's the same as half mv squared. So if we have a number of particles n per unit volume, then the thermal energy per unit volume is 3/2 nkt. And this is going to look familiar. So here we have the kinetic energy per unit volume is 3/2 nkt. Now let's consider our star. Here we have a schematic cross-section of our star. It has a total volume, big V, it has a total radius, big R, and here we're considering this thin shell at some point in the star that is a radius r, little r, from the center, has a thickness dr, and a mass within that shell of dm. Okay, the total mass of the star, the total mass within r is m. Okay, so what does that mean? Well, that means that we get our energy in this shell is given by the volume of the shell, right? Which is, we do 4 pi r squared gives us the surface area times the thickness. So we've got, this is the volume times the number density, so number per volume, times the energy for each particle. And so we can integrate this now. We want to integrate from the center all the way out to the surface. So now we have the integral from the center, r equals 0, to the surface, r equals big R, is 3/2 kT times n times 4 pi r squared dr. Okay, and we also know, so we've talked about it before, that the ideal gas law is P equals nkt, and you can see right here that we've got an nkt, and so we can do a bit of swapping out. So now we've got the kinetic energy of the whole star is given by the integral from 0 to r of 3/2 times the pressure, which is radius dependent, 4 pi r squared dr. And so basically now we want to integrate this, right? We want to integrate across this all region so that we can get the total amount of kinetic energy of the star. And remember that we also have that the equilibrium, we can get this part, we can get the P of R by integrating dP by dr, right? Because that's also something that is going to change. Okay, so again, we've got our hydrostatic equilibrium equation. We're going to want to integrate this. But what we're going to do is we're actually going to multiply both sides by 4 pi r cubed. This is just a math technique. So what we've done is we're doing the integral over the whole star to get the pressure. So we've got from 0 to r of dP dr times 4 pi r cubed dr. And here we've got, so basically I've plugged all of this in, and then I've added in a dr. Okay? But if we take this one, we can do a little bit of cancelling. So we've got a pi r squared. This will become clear later. I'm going to concentrate on this piece first. So I want to integrate this by parts. If I integrate by parts, I can get the first part, which is just the dP by dr, and that is going to be P, right? And then the other part is integrating this while keeping this straight. And so if we do this and we integrate by parts, what we get is that this first part just disappears. So at the surface, at r equals r, the pressure is 0. And so this whole term goes to 0. At the center, this r is 0, so it just goes to 0. Okay? And so that's all disappeared. And so now what we've got is that we've converted this term here to this term here. So now we've got minus 3p times 4 pi r squared dr is equal to minus rho gm over r 4 pi r squared dr. And now hopefully it becomes clear why we did this little alteration right here. So we've got this equation that is just basically taken from hydrostatic equilibrium. and we're trying to get to what the kinetic energy is. But we already showed that the kinetic energy is just what you get if you sum over all the pressure, right? And then times it by each shell. And so basically we've got all of the pressures in each shell, and what we get then is we see that these two are basically the same, but there's this factor of a half. And so we see that the left-hand side is basically 2 times the kinetic energy. So now we've got an equation that is 2 times the kinetic energy is the integral of this term right here. So now we're going to have to concentrate on this term, right? Now let's consider what happens when you have a star collapsing. So consider it being a big concentric shell of material, and you've got this material here, and it has a mass delta m that's given by its density and its surface area times its thickness. And that's the thing that's collapsing. It's collapsing from some distance s down to the radius r. Okay? This whole thing, the whole cloud, is a mass. So we've got a starting mass mr. So the mass within this radius r is m of r. This is this m of r over here. And we're going to have this shell of material fall down onto it. And this shell of material is falling from some distance s down to r. Okay? And the mass in here is, like I said, given by delta m is the density times the volume. So we know that the gravitational energy released is just the work done, right? Or the inverse, the opposite of the work done. And so it's the force times the distance. And in this case, it's this distance s, so it's the change in distance this way. And the force is just given by mass times acceleration, F equals ma. So here we have the acceleration, which is a function of the distance s, and we have the mass, which is this delta m. And so then we can put in a proper value for g. So we're basically assuming that this mass is just falling down onto a sphere that's in here that has a mass mr and a radius r. So this is what we end up with, is gmr over s squared. That's how far it's got to fall down to, and then the mass of the shell. Okay, so this is the equation we just came up with. So basically what I'm doing is I'm integrating both sides. I'm integrating this side. And so what I've got is the integral of this is then evaluated from infinity. Remember, we're dropping this material from some distance that's basically infinity down to the surface that is at r. And then we've got also the mass of the material. And so if we actually evaluate that, we end up with this, basically the change of potential energy, the amount of potential energy released in this element that has a mass delta m falling down onto a star, the core of a star, or the beginnings of a star of mr. And so now we're going to have to integrate that across all of the mass. So instead of being from just this one shell falling down from infinity to the surface, you have to do that for every shell. And so what you get is that you're integrating from 0 to big R, where that's the radius of the star, of this term here. But we already showed that we get an equation that 2 times the kinetic energy is given by basically the same thing. And so if we equate those, what we get is that the kinetic energy of a star is half the potential energy that went into forming it. And that is Virial Theorem. There are a couple of consequences of Virial Theorem that we should talk about. First of all, what it basically says is that half the gravitational energy of collapse has to be radiated during the collapse process. So you've got a certain amount of energy in the cloud, and as it's collapsing, that energy has to be released. Half of that energy has to be released. The other half is converted into the kinetic energy, and that's what gives us the energy to start fusion eventually. This means that once it reaches hydrostatic equilibrium, once you've got your star, it has to have negative heat capacity. That is to say that it gets hotter by losing energy. So let's just consider this. We've got a total energy, which is the potential energy plus the kinetic energy, but the kinetic energy is negative half of the potential energy, so it's half the potential energy, which is a negative kinetic energy. So basically, by losing energy, the star gets hotter. Isn't that fun? And that's all we can talk about Virial Theorem for now. We'll come back to it when we study how stars form again in Star Formation Part 2.